It is truly an honor to have Roland Green with us today. He's an alum of UTSA, a fellow Roadrunner, and he's been doing some phenomenal work as a computer architect and performance engineer at the Silicon Valley startup Cerebras Systems. He primarily works on the performance team, where he's responsible for developing performance analytical models for machine learning models and developing tools to assist with performance projection and debugging. Prior to Cerebras, he was a PhD fellow at Purdue studying GPU microarchitecture, simulation, and modeling. And he did his undergraduate study at UTSA in the ECE department. An honor to have you here, Roland, today. Looking forward to your presentation. The floor is yours.
Great. Thank you so much for the introduction. It really is great to be back, even if only virtually for now. Yeah, and it's I'm really happy I get to share some of the really cool stuff we've been doing over at Cerebras Systems over the past couple of years. So today we're going to be talking about, or what I'm going to be talking about, are some of the really cool ways where we're enabling the training of giant neural networks using our new weight streaming execution mode. So just to provide a little bit of background on Cerebras Systems itself, if you're not familiar with the company. So we started in 2016, and our mission from the outset was to solve the problem of AI compute. In 2019, we introduced the wafer scale engine, sometimes referred to as the WSE, which is the world's largest chip, beating the second largest chip by about 56x. With this design, what we're really allowed to do is we're allowed to deliver cluster scale performance from a single chip. Now, since 2016, we've of course grown quite a lot. So we make up over 350 engineers in 14 countries. We've got offices in California, in Silicon Valley, in San Diego. And then we also have a few international offices in Toronto and Tokyo. And as far as customers go, it's really great to see that we're covering more and more of the globe here with customers in North America, Asia, and Europe. So on to kind of the star of the show here, which is the WSE2, which we announced earlier in 2021, which is our second generation wafer scale engine. This is a single chip that we have with over 46,000 square millimeters in size, with 2.6 trillion transistors at TSMC's 7 nanometer process technology. So this is a really incredible number. It's 850,000 individually programmable AI optimized cores on this thing. I can't help but smile every time I see a picture of the full chip. I've been trying to get my hands on one for quite a while, one of the older ones. So we do more than just a chip, of course. The chip has to go into something. The wafer scale engine is really at the heart of our Cerebras CS2 system, which is the world's most powerful AI computer. So this is when we have a customer, or what are they actually running on? They're running on not just a chip, but this entire CS2 system. But we do more than just, we do more than hardware, right? We also have to write the software that enables customers to use our CS2, and by extension, the underlying wafer scale engine. And that's where this Cerebras compiler comes in. So customers, they have their models written in, familiar frameworks like TensorFlow or PyTorch. And through our Cerebras compiler, we're able to take these models, optimize them, and map them to the hundreds of thousands of cores on our wafer scale engine. Now, in the past, what a lot of the presentations have focused on is a different mode of execution, this pipeline parallel mode of execution, where we take a model, we match it to these highly optimized layers, perform a place and route process, and put them all onto our fabric, and then stream in data and stream out losses. But today we're going to be talking about something that we introduced late last year, or last year, and talked about a number of times, which is this new mode in our software stack called weight streaming. And the main kind of key feature about this weight streaming mode is that we're trying to enable the training of giant neural networks. So to give you a little background of why we care about these giant neural networks so much, we can look at some of the scaling trends of these neural networks over just the past couple of years. So in the past 3 or 4 years, state-of-the-art language models have increased in size by about 3 orders of magnitude, which is a huge amount. So what's considered state-of-the-art in terms of something like BERT, released in 2018, has hundreds of millions of parameters. That was considered extraordinarily large at the time. However, if we look at much more recent models like GPT-3, we're talking about models that have hundreds of billions of parameters, right? So tens or hundreds or 1,000 times models, or 1,000 times larger than models that were state-of-the-art just a couple of years ago. Now, with these larger models, you're of course going to need a lot more compute in order to train these models, and a lot more storage for the model parameters. So in fact, when we're talking about the compute requirement is actually increasing about 12 times faster than silicon performance increases under Moore's law. And Moore's law is, as everyone likes to talk about these days, everyone talks about the end of Moore's law and Moore's law scaling. So this is quite a scary situation to be in. We've got compute requirements increasing faster than something that we're saying is ending. So feasibly, training a model of such enormous size requires scaling out to a very large number of workers. So for example, something like GPT-3 was trained on a cluster containing thousands of GPUs. However, existing methods for scaling out really falls short for large models. The primary reason for this is that it's complicated to implement, and it still constrains model size. And that's what we're really going to dive into in the first half of this slide deck. Okay, so in order to really understand kind of the scaling problem, we need to talk about the strategies of training with locally stored weights, right? And see kind of the pros and cons of these different approaches and how they can limit scaling. So in general, the common approaches for training involve storing the model parameters, including things like weights and gradients and momentums in the worker's compute memory. And we're talking about a worker. We're talking about usually some sort of accelerator like a GPU or something like the wafer scale engine. So in terms of where this is being stored for something like the wafer scale engine, it's being stored on chip in the very fast storage that's on chip. In the case for something like a GPU, it would be in something like DRAM. Now, training is scaled out to multiple workers, primarily to reduce training time. Right? So, either we split the training batch between workers, and this is referred to as data parallelism, or the model is split between workers, which is in turn referred to as model parallelism. So these approaches have worked, and they've shown to work very well in a number of different situations, especially when the model fits in the memory of a single worker. So something like a CS2 or something like a GPU chassis. So a number of GPUs grouped together and tightly clustered. However, how well these strategies work, it really breaks down when you expand it to something like GPT-3, right? Or these enormous scale models. So data parallelism alone runs into memory constraints, and model parallelism suffers from massive communication bottlenecks once you get to a very large scale. So let's start by introducing some terminology that's going to be used to describe some of the requirements, both in terms of compute and communication in the following slides. So, we have a neural network that's composed of, let's say, L layers, where each layer uses parameters to transform activations. Each layer itself is composed of H features. Now, the value of H change throughout the network. But for transformer models, which we're primarily talking about in the slide deck, the number of features expands and contracts between H and 4H in the feed-forward portion of the model, but otherwise remains constant. So for simplicity, we'll just leave this as H. So training, of course, is performed in steps, and weight updates are applied at each step using gradients computed on a batch of training data. And each of these batches is composed of B samples from the training data set, which is usually much larger than B, right? So we usually have much more data than our batch size, of course. And then on the right-hand side here, we're trying to parallelize this thing over in workers using one of the techniques that we've talked about in the earlier slides. And we'll go into those techniques a little bit more to understand their limitations. So we'll start out with maybe the most intuitive way to decompose a problem like this, which is data parallelism. So in data parallelism, a full copy of the model is placed on each worker. And then the training batch is split evenly over the workers such that each worker gets a unique shard of the batch. So if we look over here, you see every single worker has L layers, so they have the entire model, but they get, since we have 4 workers in this case, represented by these 4 boxes, each of them gets B over 4 activations, right? Now, this is pretty simple. So each worker computes activations and partial gradients for its shard of the batch, its B over 4 activations. And then before the weight update occurs, what we have to do is we have to do this gradient sync to make sure that each of the workers has a consistent copy of the model as training progresses. So even though we've split this, from this diagram to say 4 copies of the model, we're still training that one model. We're just, for performance reasons, we're splitting it across a number of different workers. So this is often preferred style of parallelism, primarily because it's very simple, right? It's very intuitive, but it also has constant communication here that's independent of the batch size here. So in this case, communication is proportional to the model size, right? It's just these gradients that have to be communicated across all of the different workers that we're splitting across. We're splitting the batch across. However, it becomes limited for large models by the memory capacity of each worker. So you'll notice here, every single one of these workers takes the entire network, takes all L layers, right? Which can be enormous when we're talking about very large models like GPT-3. So even though we're splitting something like, say, the batch and the number of samples that are going to, say, each worker, that's really only decreasing the activation component, but the whole model is still stored on each worker. And when we're talking about models the size of GPT-3, which require terabytes of storage, they simply won't fit on a single worker, which is usually limited to something like tens of gigabytes of memory. So this makes data parallelism an insufficient solution on its own, right? You can't possibly fit an enormous model on a single worker using this strategy. So an alternative to something like data parallelism is model parallelism. So model parallelism basically means splitting the model between workers. And this is something that can be done in a number of different ways. And we'll look at 2 approaches in this case. So tensor model parallelism is one approach where each layer is split across multiple workers. So here, again, we have the same 4 workers, but this time, instead of every single worker getting the entire model and having to do that gradient sync, now each of these workers is going to work on 1/4, say, of a layer at a time. So if we have an enormous layer, we can split it across, say, multiple workers. Now, this enables training of, very large models, right? Because now now we're able to split parameters across multiple workers. However, now we have to deal with this communication. So this communication step is going to be required between the computation of each layer's activations. So for example, if we're talking about something like a fully connected layer that can be split on, say, its input features, then computation of output features would require a reduction between all of these workers. Likewise, you could split along the output activations, but this would mean that the input would need to be broadcast to all the workers. And then, of course, you can reduce the communication by making things even more complicated. So you could split across both the input and output feature dimensions. But in all these cases, we're talking about communication that ends up being frequent, and the volume of communication that we're going to basically induce through this approach does not decrease as quickly as computation with scale. So communication ends up really becoming a bottleneck here. So as we move on to another kind of model parallelism, we're going to talk about this pipeline model parallelism. So in this approach, right, we can group contiguous layers, or we can take groups of contiguous layers and split them across workers. So instead of, say, every single worker getting a full copy of the model, we'll say have, 1/4 of the model go to one worker, the next 1/4 of the model go to the next worker, and so on and so forth. So as each worker computes its activations for its final layer, it passes it to the next worker, right? So we basically just created a pipeline for our network. In the backward pass, the activation gradients then from each worker's first layer are passed back to the previous worker, right? So we have activations flowing in one direction and then the activation gradients flowing in the opposite direction. So with this approach, right, we have less frequent communication than tensor model parallelism, or than the tensor model parallel approach, when the number of workers is fewer than the number of layers. However, as we increase the number of workers, the communication requirement approaches tensor model parallelism. This also tends to have a limitation of your number of workers being capped with the total number of layers in your network. And this is because, you could split, some layers across multiple different workers, but it really starts to make things much more complicated once you start fusing these different kinds of parallelism, which we'll see in the next slides. Another really difficult part about this approach is that we have created a pipeline. So now we have to get into the game of pipeline stage balancing, right? The performance at steady state of this network, right, on whatever platform we're running on, a wafer scale engine or some other kind of dedicated accelerator, is going to be dictated by whatever the slowest stage is, right, steady state. So it introduces another layer of complexity and makes it much more difficult to scale out. So as I mentioned earlier, we of course have hybrid parallelism, which is really what is done in practice, right? This is really the only way you can train something like GPT-3 on modern hardware and really get that balance of, getting something that can actually run on modern hardware and also, try to get better performance. And we're talking about here a mixture of data parallelism and model parallelism. So with model parallelism, we can bring the per worker memory requirement down to something manageable. And then the data parallelism is there to provide the additional scale for compute without increasing communication overheads. But as you probably could have guessed based upon all the previous terms we've introduced, this makes things pretty complicated, especially when both these types of parallelism are involved. Because there can be different types of communication and different workers performing different operations. So balancing all of this stuff is incredibly complex and incredibly difficult. So training something like GPT-3 really takes somewhat of a Herculean effort. But, we can also notice from everything I've talked about so far that all of these approaches share the same kind of central problem, where the model size, at least in some form or fashion, dictates the size of the cluster that we need to run this on. So in all the approaches that we've looked at so far, we're talking about storing model parameters locally, which we refer to as store-based training. This means that the number of workers in is partially dictated by the model size. So larger models, of course, require more workers. But this isn't ideal, right? This is ideal because the number of parameters doesn't map directly to the compute requirement. You can have a model with lots of parameters, but that doesn't necessarily mean that the compute is going to be so much more than, say, some other model with a smaller number of parameters or fewer parameters. So for example, right, the same model is typically pre-trained on a very large data set and then fine-tuned on a smaller data set for a specific task. And aside from the memory requirement, it doesn't make sense to fine-tune a model on the same size cluster used to pre-train that model when the compute requirement is far less, right? So you don't want to cluster 1,000 GPUs to do fine-tuning on some model. So similarly, there's aspects of the model architecture which control how much compute, of course, occurs per parameter. So if we're talking about something like sequence length inside of a transformer model, that'll change the amount of compute in the attention layers, but it does so without changing the number of parameters, right? And on top of this constraint, getting models of this size to fit, it requires implementing complex hybrid model and data parallel systems, right? It's just not possible to even train them otherwise. So, a real key here is this idea of decoupling memory capacity and compute capability of the training solution. And, we've created a new execution model to do this that we've called weight streaming. So that's what the remainder of this presentation is going to be focused on. So the idea is we're going to take what's traditionally been this complex and intertwined problem of distributing memory, compute, and communication and synchronizing all of them at the same time and separate things out. So similar to the training data set, which is commonly stored externally from all the compute workers. So you're not storing, say, your entire training data set on the GPUs. We're going to move the model parameters into an external memory service, fundamentally disaggregating compute and storage, or compute in this case, which is going to be our wafer scale engine, is going to be separated from the storage of the massive number of parameters for models like GPT-3. So the bulk of computations, including things like activations and gradients, are still going to be handled on the wafer scale engine in CS2. Which is our compute worker in this case. So when we're talking about compute workers, in the case of Cerebras, we're talking about the wafer scale engine. Activations are stored locally on the wafer scale engine, where they can be accessed with low latency for the next layer's computation. And then weights are streamed onto the wafer scale engine from the memory service as the layers execute. Computed gradients are then streamed back to the memory service, where weights are updated. And this relatively low frequency access for parameters gives plenty of time for weights to be updated on the memory service between training iterations without introducing things like pipeline bubbles. And this really allows us to get really high utilization out of our wafer scale engine and keep it busy basically at all times. So weight streaming allows us to train these giant models with memory scaling to meet the requirements of the model. But we still need a way to parallelize training over multiple workers, right? Allowing compute to scale with the requirements of the workload. So weight streaming can be combined with either approach, right? This model parallel or this data parallel. Data parallelism splits the training batch between workers, combining weight streaming with data parallelism involves broadcasting the weights to all workers and reducing gradients from all workers before updating the weights. And then with something like tensor model parallelism, it splits each layer over multiple workers. Combining this with weight streaming involves sending unique shards of the weights to each worker and receiving the corresponding shards of gradients back, of course. Or back. Of course, model parallelism also requires communication directly between workers to broadcast and or reduce these activations here, as you can kind of see on the right here. Let's see. When it comes, just saw a question in the chat. When it comes to fabric design decisions, can you please give us a high-level overview of the decisions you made designing the scalable masterpiece? So actually, after we talk about weight streaming for a bit, there's a bit more of the design of the data flow. I'll cover a bit of the data flow architecture itself to understand how weight streaming actually executes on the chip. But great question. So, into what we've actually decided for weight streaming, we've chosen to focus weight streaming combined with data parallelism in our architecture for a number of reasons. So first of all, we no longer have the need to split the model between workers, which is one of the main reasons for using model parallelism. And then second, there's no additional communication required when compared to stored weight data parallelism. The communication required to all reduce gradients between workers is the same as the amount of communication required to broadcast weights to each worker and reduce gradients from each worker. On the other hand, combining with model parallelism would mean that both weights and activations are communicated, increasing the total bandwidth requirement. Data parallelism also allows us to avoid any of the communication delay between layers. The only communication dependencies occurs really between training iterations. And then finally, data parallelism is simply it's simpler, and which makes scaling a lot easier. Very complex things tend to not scale very well. There's no need to worry about how layers or fragments of layers map to each worker. But what we need is an interconnect to handle the broadcast and reduced communication required by weight streaming and data parallelism. So that's where two new components that we've introduced at Cerebras come in. So we've developed two new components to support weight streaming in the roles of a memory service and an interconnect. So first of all, we have MemoryX over here. The MemoryX technology provides storage for model parameters and compute for running the optimizer and updating weights. This can be configured between 4 terabytes and 2.4 petabytes. So it's really to support models of any size. To handle the broadcast of the weights to each CS2, so for something like a cluster of CS2s we have over here, and reduction of the gradients from each CS2, we use SwarmX fabric. So SwarmX fabric can provide enough bandwidth to scale up to 192 CS2s, which is quite a big cluster, especially of these giant chips and systems. Broadcast and reduction operations are accomplished with the tree topology to enable modular and low overhead scaling. And because it's modular and disaggregated, it enables scaling to multiple CS2 systems with exactly the same execution model as a single system, which is really great. And we really try to keep things simple here in order to enable effective scaling. From the perspective of a CS2, SwarmX fabric is indistinguishable from MemoryX technology and vice versa. So, we're talking about exactly the same system architecture, the same execution flow and software, and the same user interface. So whether you're programming one CS2 or a cluster of CS2s, it looks the same to the end user. Scaling to more compute is as simple as adding more nodes to SwarmX topology and adding more CS2 systems. So there are a couple more questions here. Are the computations being orchestrated dynamically or statically? So in general, they're orchestrated statically. It depends what you mean by which computations, though. In terms of high level, how the model is executing, we'll talk about that in a little bit as well when we get into how individual layers actually execute on a CS2 system. But basically, your model itself, right, is a predefined graph of compute that you're going to be executing. So from in that perspective, it's fixed. However, because it's a data flow architecture, some of the decisions of what compute happens and what compute does not happen depends on value somewhat. And we've designed we've designed an architecture specifically to handle or specifically for sparsity harvesting. So, for example, whether or not compute happens will depend on whether or not a value, say, is 0 or not. let's see, compute complexity also depends on resources assigned to workers. Shouldn't the number of resource of each worker be accounted in deciding which model is efficient? I'd have to ask a number of more questions for that, but I'll keep that in mind. Maybe that's a question that's better iterated on offline. And for time constraints, maybe we'll try to get back to the end, but I'll try to get through the remaining slides first. Okay, so let's talk about wafer scale kernels. So we've talked a lot about the kind of the high level of how these, how weight streaming works conceptually. But let's talk about how, say, a kernel in this weight streaming mode would actually execute. And it all starts, kind of at the very lowest level when we're talking about the individual PEs. So as we kind of said earlier, the wafer scale engine is still doing all the heavyweight computations needed for training. So things like the activation compute on the forward pass, the weight gradients on the backward pass, and the activation gradients for back propagation. And the wafer scale chip is, of course, being an 850,000 core chip is ideal for training large models. So the massive core count and bandwidth delivered by the 2D mesh fabric means that it can be used to execute any size layer. And this means no partitioning of layers is needed to achieve reasonable compute times, right? Simply because of how enormous the chip is. Secondly, because this is a data flow accelerator, the data flow execution built into the architecture really meshes well with weight streaming specifically. So incoming weights trigger work on each core, so they're never stored persistently. And that means there's really no upper bound on the size of the weight matrix, assuming that the activations fit, right? All of the weights are really just being streamed through. They're not being permanently stored on the fabric. So it's really things like the activation size that's going to be the limiting factor for what models can be supported. And even in that cases, there's ways that we can work around when activations start to become a limitation. So in terms of data flow scheduling, it also means that we can take advantage of sparsity in the weights in order to reduce training time. So compute's going to be triggered for only non-zero weights, and communication only occurs for non-zero weights. So this works for high degrees of sparsity and even for dynamically changing or unstructured sparsity. And it works at full utilization. And the really important thing about this is that there's really no other architecture that can efficiently do this, right? This is a very purpose-built architecture for handling, AI workloads, and it was designed exactly for this task. So, a number of active research in the area has shown that weight sparsity can provide, really significant flop reduction without, causing a loss in accuracy. And this is really something that we think as being the key for training much larger networks in a reasonable amount of time. And we're talking about these GPT-3 multi-100 billion parameter networks, multi-trillion parameter networks. So in weight streaming, we execute layers one at a time, as opposed to something like, let's say, like a pipeline mode where different workers are executing parts of a network at the same time. So in this case, the full wafer computes activations for a layer, then moves on to the next layer, which really means that the compute work is spread over the entire wafer. So we can really use those 850,000 cores to speed things up. But how exactly do we do this? Since we want to minimize data movement, computations are performed on the cores where the associated activations are stored. And this really allows us to leverage the full 20 petabytes per second of memory bandwidth for accessing activations. Achieving this means we have, but in order to actually achieve this, you've got to be pretty strategic about the data layout on the wafer. So for transformer models like Megatron or GPT, activation tensors have 3 logical dimensions. So a batch, a sequence, and then a hidden or a feature. We split these tensors these tensor dimensions over our 2D grid of cores on the wafer. And in this case, the hidden dimension is split over the fabric X dimension. And then the batch and sequence dimensions are split over the fabric Y dimensions. So and H being the features, and B being the batch, and S being the sequence over here. Let's see. And sequential chunks of the sequence dimension are going to be on, of course, adjacent cores. So, with this arrangement, this allows for efficient weight broadcasting and reductions over the sequence and the hidden dimensions. For very large batches, we can split the batch into a small number of chunks and perform this mapping on subrectangles on the fabric tiled in the X dimension. Right? Okay. So with activation stored on the cores, where the actual work is going to be performed, we need a way to trigger computations for those activations. So in our architecture, data is moved in these 32-bit packets called wavelets. And in the WSC architecture, work is triggered by incoming wavelets. So for weight streaming, work is triggered either by data wavelets containing weight values or command wavelets. These wavelets are broadcast over columns of cores, and these weights directly trigger things like the FMAC operations, which these FMACs are really the core of machine learning and the core of these workloads. Since the broadcast occurs over columns, all the cores containing the same subset of features are going to receive the same weights, as is shown here. Command wavelets trigger all the other computations here on activation buffers, such as reductions and nonlinear operations. Commands and weights are sequenced jointly by the driver running on the memory X units and a coordinator server, meaning that much of the control flow is offloaded here. So because these computations are being triggered itself by the data that's arriving at these cores, it's very different than, say, your traditional kind of CPU architecture that has to worry about loop overheads and indexing. It's being triggered directly by the data. So let's walk through an example a little bit more with the very common kind of kernel that you'd expect in a machine learning workload, and really sits at the core of most machine learning workloads. So for something like transformer, one of the core operations is going to be a GEM operation between the weights and the activations, where GEM, of course, being general matrix multiplying, where weights and activations are each treated as a matrix. And then for activations, this is done by flattening the sequence in the batch dimensions. So weights are sparse and streamed from off wafer, right, from that memory X that we talked about. And activations are residing on chip, in the on chip memory, so in that SRAM on chip. So we execute a GEM as a series of GEMV operations. So matrix vector multiplies, right? Matrix multiplication is basically just a bunch of GEMVs. And this is key to achieving a full utilization, the presence of unstructured sparsity. So for each matrix vector multiply, a row of the weight matrix is sent to the wafer. That's our vector. And then this row of weights is split over the fabric X dimension in a distribution that matches the activation storage. This means that when the weights arrive on the columns where the associated activations are stored, this means that the weights arrive on the columns where the associated activations are stored. So in the diagram over here, H0 over here refers to the input features, and H1 is going to be output features. So each matrix vector multiply computes one output feature for H1. So weights from this row arrive sequentially in a stream of wavelets. So wavelets being those 32-bit packets that get sent across the fabric. When a weight arrives, it triggers that FMAC operation on the core, right? So it's this data flow trigger. Wavelet arrives based on that wavelet, it triggers some computation there. The index value of the received weight is used to look up the corresponding activation value for each token in the local portion of the batch. The weight value is multiplied with each of these activations and added into the accumulator over here. So this data flow scheduling and tensor memory access features of the architecture, they really allow for this operation to be done with zero overhead on the core. So like I was saying earlier, there's none of this looping overhead. There's none of this address calculation overhead. That's all being done automatically and being triggered by, the format of these packets. It's because of this zero overhead, vector scalar support that we can officially accelerate this unstructured sparsity. Now, once all the weights for a row have been received, each core contains a partial sum vector, which needs to be reduced within a row of cores. So this reduction is triggered by command wavelets. We had data wavelets, now we're talking about command wavelets, which is received on each column. All but one column receives a partial sum, or noted as a p sum in this case. One column of cores gets a special fsum command, indicating that final reduced results should be stored on that column of the cores. This is necessary so we can store the output features using the same kind of distribution as was used for the input features, setting us up for execution for the next layer. Now, upon receiving these commands, the cores within the row initiate communication using a ring and compute reduced final sums. The final sums are stored in the column which received the fsum command at a memory address indicated by the wavelet. Now the wafer, now the wafer is ready to process the next row of weights. And then after all the rows of weights are processed, the full GEM operation is complete, and all of our activations are in place for the next layer, and the next set of weights can stream in. So, a very kind of intuitive question about this is, we've been able to, get around the fact that, we have these enormous amounts of parameters that are a real limitation for most other, or every other accelerator by not storing the weights on Fabric. However, we are now storing the activations on Fabric. So a natural question is, well, what happens when the size of these activations becomes enormous, right? And they won't all fit on Fabric. So we'll talk about a few techniques in order for wafer scale memory management. So memory on the wafer, it's used to store activation buffers for the forward pass or from the forward pass, which is needed for the gradient computations on the backward pass. So each core has direct access to its own local memory. And in total, the wafer scale engine contains about 40 gigabytes of on-chip memory. So this provides, enough activation storage for many networks, but it does become limiting if we must store activations for every single layer in a giant network. So in order to make the solution work for any size model, not just ones that will, we can fit the activations for every single layer on Fabric, there's a couple of techniques that we can use in order to reduce the activation memory requirement. So the first, of course, is reverse checkpointing, which is a pretty common technique. So we can store just a subset of the activation tensors computed during the forward pass, and then during the backward pass, we recompute the intermediate tensors. So one kind of sweet spot involves storing the number of checkpoints equal to the square root of L, being the number of layers. And using half the memory for checkpoints, we recompute the intermediate layers and store them in the remaining half of the memory that we have on chip. So in total, this means we reduce memory requirement on the order of square root of L at only a 33% compute overhead, where this 33% comes from the fact that we're recomputing activations once for most layers, but not the weight or activation gradients. So if we kind of look at this diagram over here, each of these orange dots over here, these represent activation compute. And then the purple dots over here, these are going to be the gradient computations. Now, this top line, of course, marked as such is a forward pass. This kind of greenish blue line is the backward pass. Now, these, let's see, so these orange dots over here, right? These are going to be strategically placed, and this really represents our recomputation, right? And these lines going down are going to be our activation buffers stored between checkpoints. So we can strategically kind of choose these checkpoint locations to avoid recomputation of the expensive layers. So something like attention. Now, all of these, this seems like a pretty complex process here. But the kind of key point to all of this is this isn't something that has to be managed directly by the end user. This is something that's handled by the Cerebrus compiler without any change to the user's model code. So another technique we can, of course, employ outside of something like recomputation is evictions. So for very large networks, we can send activation tensors off wafer and back to the dataset server for long-term storage. And then on the backward pass, we can bring this data back onto the wafer. Now, of course, we've introduced more communication here, right? So we have now additional communication, but the dataset servers provide enough storage for any practical number of checkpoints. And this tends to work for very large layers because the compute increases quadratically with the feature count, but the communication only increases linearly, right? So you're still going to be compute dominated, even though you're adding this extra term for this communication, for evicting and having to bring things back onto the wafer. So by reducing the number of activation buffers live on wafer, using these two techniques of recomputation and also eviction, we can run even deeper models. But we can also run at higher utilization. So placing a larger batch on the wafer helps to overcome communication and other overheads, right? You're amortizing all of these costs over this larger batch size. So all the optimizations, all of this optimization, considering these trade-offs, is handled automatically by our compiler still. So again, both of these things like recomputation and this eviction process, this is not something that users have to spend a whole bunch of time figuring out how to coordinate. It's handled by our compiler and runtime systems. So of course, it's great to have a whole lot of talk about some cool thing, but it really comes down to where the rubber meets the road, right? And what does performance actually look like for something like weight streaming? So on the side, we've got a graph that shows utilization we've measured in our lab across various model layer sizes. And we're talking about these very large models going all the way from something like GPT-2 to GPT-3 to these 1 trillion parameter models. And we're talking about these enormous model layer sizes here. So, we're talking about square matrix dimensions of, 16K by 16K or 32K by 32K. Now, for smaller layer sizes such as GPT-2 all the way up to these extreme layer sizes, like in these 1 trillion parameter models, we're seeing roughly the same very high utilization. So utilization in the 75 to 80% range across the board with the same workload mapping. And the reason for this is it's simply because the wafer scale engine, right, that 850,000 PE array of cores, it's large enough to fit these enormous layers up to these 100K by 100K matrices. And this is something that we also get the benefit of, unlike things like GPUs, we don't have to split, say, this matrix multiplication across multiple devices and have this extra communication. It can all happen on the single device. During activation recomputation, is there any loss of information, or does it recover original activations completely? It should recover it completely, right? It's just a pure recomputation. It's just a storage saving. So the techniques we're talking about are without a loss in accuracy. I'm sure there are ways to save even more memory with more lossy styles. Like there's compression techniques that you can look at that do provide potentially a decrease in accuracy for more memory savings. But no, these should have no loss in accuracy. So weight streaming as a solution, it also scales well across multiple CS2s. Since we can add nodes to SwarmX Fabric to meet the broadcast and reduce needs of many CS2 systems, the scaling performance is near linear. So we have a plot here that shows solution scales to multiple CS2s, where each line represents a model size from 10 billion to 100 trillion parameters, where the x-axis is going to be the cluster size down here, and then the time to train on the y-axis over here. So models that contain hundreds of billions of parameters, which were once prohibitively difficult to train, can be trained in hours on very large CS2 clusters. And then vastly larger models like those with trillions of parameters, which would not be possible to train today, can be unlocked with solutions like this. And these projections are based on 90% weight sparsity, but the solution can provide acceleration for even greater degrees of sparsity, because from the ground up, this architecture was designed for sparsity harvesting. This is really the scalability of this solution, both in terms of memory capacity and compute. It's always kind of a thing that you always want to avoid saying, but it does make it future-proof in some way. All right. So we've seen the massive increase in size and parameter counts for these models over just 3-4 years. So we really need a solution where we're not thinking about how do we support, say, a trillion parameter model. We need to already be thinking about how do we support something like 100 trillion parameter model, because that might be where state of the art is a couple of years from now. So it looks like we have a question. What is the difference between the weight stream approach and input stationary data flow approach commonly used in AI accelerator? What are advantages of weight streaming over activation streaming? What is energy consumption of CS2 to perform large model such as GP2 or GPT-3? I don't think I have any numbers on the top of my head in terms of the actual energy consumption. In terms of the differences between the weight streaming approach and input stationary data flow approach, if you check out either the beginning of the talk, we mainly talked about the limitations of the current approaches, which are used by GPUs today for training things like GPT-3, which is it is a weight stationary approach where weights are resident on accelerators, and the hybrid approaches of model parallelism and data parallelism. That was kind of the focus of the first half. There's also, for more information on that, it's probably, it could be also a great thing to look at we have a white paper on weight streaming that's available at Cerebras.net. So if you just look up the title of this talk in Cerebras, you should find in the first 1 or 2 links from Google a link to that white paper. So that'll also provide the same information I gave at the beginning of the talk. Let's see. And I think we're on the last slide here. Yeah, so it's been really great in order to come here today and answer some of the questions provided by you guys, and then also present some of this amazing work that we're doing over here at Cerebras. As research, comes up with these really amazing models to do amazing things. So things like AlphaFold 2, GPT-3 and beyond. What we're seeing is extraordinarily valuable applications coming in the wake of this research. but these applications require an infrastructure that can support training multi-billion, multi-tens of billion, multi-hundreds of billion, multi-trillion parameter models, things that work at this huge scale. And this weight streaming architecture that we talked about today is a practical solution for these enormous models of both today and the upcoming models that will be even larger than what we're seeing today. So, weight streaming really makes the engine the ultimate scale out accelerator, as well. So with this kind of horsepower of an 850,000 core chip and a multi-million core cluster, really the possibilities are endless. So come up with all the amazing models you can think of that might not seem possible today. Of course, if anyone has any questions, you're more than welcome to follow up with me either on LinkedIn. Feel free to message me. I would also be happy to provide my email. Of course, please check out Cerebras.net. Tons of job listings there. So if you're in the market, we're always looking for amazing people to come work with us and help work on the world's largest chip. We've also got quite a bit of information, including blog posts and technical white papers there that you can read about. But yeah, it was great coming today, and very, very happy to be here.
Thank you, Roland. That was a great presentation and very informative. I'm sure our ECE students are really delighted to have those details on how you are optimizing at various levels in order to get to train these large-scale models. Beyond some of the questions asked here, I know a lot of examples that, for some of the models maybe is more on the static images or static data processing. What do you see as a complexity when your input streams are more going to be spatiotemporal? Do you see some of these mechanisms scaling up for spatiotemporal data? And especially with training, storing all your activations on and training on device. How do you see the complexity scale?
Yeah, I think there's a lot of work to be done in terms of making this a more robust solution and handling different circumstances. I mean, even in terms of supporting things like variable sequence length in models can be another challenge, and that's certainly something that we're not necessarily handling today, but something that we're working on in the background and working on supporting in the future. I don't have a great answer to the question, unfortunately. Most of my work, it tends to be on the performance side of things and the architecture side of things. So on the in terms of the contemporary ML, I'll be less knowledgeable, but I'm sure I could reach out to somebody at Cerebras to provide a much better answer.
Thank you. In terms of performance for the current models, like in terms of using on-device training, right? You've given examples of these large-scale models. And of course, you've shown the variety of models that we have. Some of them may not necessarily have these trillions of parameters, right? Mm-hmm. There is this other movement to compress the model size and have fewer parameters to get to the task you want to do.
Yeah.
So with such heterogeneity in the models that's going to be there in the future, even more, I feel that heterogeneity is going to spread. How do you see the CS2 working for both types? Do you see that it's going to be targeting only these large-scale models, or do you see a path where it can be advantageous maybe in certain cases with these smaller models?
Yeah, so I think that's a really great question because, while everyone likes to talk about something like GPT-3 or these enormous models that, are really only possible for hyperscaler companies today, a lot of work in terms of being able to iterate on smaller models is where a lot of great research and great engineering work gets done. Now, while we've had this weight streaming work, come up and running to support these large scale models. Things like our pipeline execution flow, where weights are resident on chip, is one way that we're handling things like medium-sized models, like things like BERT base, BERT large, Roberta, things like that. But yes, you also run into this situation where you have where you have the very small models that you simply can't stretch. But in the same way that you can do the model and run multiple copies in parallel and split a batch, say across multiple different GPUs, you can do the same thing and get some pretty enormous advantages about for partitioning the fabric and running multiple copies of the same model on the same fabric and doing everything, including the communication between these models and the gradient sync, all on the same fabric. So you can really get some amazing speed ups with an approach like that. And given that we have this giant fabric like this, it also opens up the possibility, if you wanted to do something like maybe you don't want to just train one model very quickly, but you want to train multiple models in parallel, right? So you can get higher utilization, not by, trying to get higher utilization on a single model, but maybe training 10 models at the same time or 16 models at the same time, and just partitioning the fabric in order to support that.
That's a great point. Thank you so much. I know we are a little over our time here. Thank you for sharing your insights with us today. And we'll be posting this video on YouTube shortly. And some of our students might have questions for you, Roland, seeing your success and how well you're doing and all the great work you're doing at Cerebras. So we'll follow up with that. Thank you.
Yeah, that sounds great. And yes, I encourage anyone, don't be shy in terms of asking questions. I'm more than happy to speak with you. So please reach out if you have any questions.
Have a great day, everyone. See you next Friday. Bye.